Johnny here with Simpson Math, and in this video we're going to begin transforming the trig functions. Specifically in this video we're going to be focusing on the dilations. Now off to the right over here I have a function written down where I have A, B, C, and D, and these are all the different types of transformations that we might come across. And this should not be new to you. You should have dealt with the transformation rules in a college algebra setting. I'm just going to walk you through them again in the pre-cal or trig setting. But this f here, for like f of x, this function notation, that f can represent any function. Something you're more familiar with, like a square root function, a rational function from college algebra, or now with the 6 new trig functions. So f could be the sine function or the cotangent function. And we're going to focus in on A and B today, where A is just going to affect the height of our graph. So it'll take our functions and we'll simply take the y values of the parent function and multiply them by y. So if we have a value greater than 1, it's going to stretch it, vertical stretch, upward and downward. If that a value is less than 1, not negative, but something like 1/2, 2/3, it's going to take our function and again still multiply the y values by that number, a half of all those values, or a third of all those values. Those are going to compress the graph vertically. B is very similar, but it kind of does the opposite of what we want. If I have a 2 on the inside, we're actually going to go through and multiply by its reciprocal 1/2. So a 2 on the inside takes my trig function and it's going to compress it horizontally, whereas a 1/2 on the inside would stretch it out and double it horizontally. All right, let's go through the motions. I'm going to start off with a sine graph. And in the previous video, I graphed all of my trig functions starting at 0, and then I showed one period. In this video, I'm going to change things up a bit. I'm going to show that same period, but over a different interval. So I know sine has the point 0, 0, and I know it's pretty at the 6's. In quadrant 1 and in quadrant 2, so at pi 6 and 5 pi 6, we have the sine value of 1/2. Sine of pi halves is positive 1. And when I get to pi, the sine value is back to a y value of 0. Sine of pi is 0. And you can see the sine wave starting to form. And I would continue going on to the negatives, but instead I'm going to start looking at the negative region. You can think of this as quadrant 4 or maybe quadrant -1. Sine of negative pi 6. This is going to be -1/2. The same is true for -5 pi 6. And at 270 degrees or -90 degrees, we've got a sine value of -1. And negative pi is the same thing as positive pi. They are coterminal, so the sine value is 0 also. This is my parent function, sine. I've just graphed it over a different interval. I'm not going to fill in the graph. This is not where I'm trying to get to at this moment, but I'm going to do a little dotted line just to help me see the parent function sine of x. What I'm about to do is transform it. I'm going to put a number, like a coefficient, on this sine wave and just see how it affects my graph. So in a different color, I'll choose orange. I'm going to come over here and say I'd now like to graph y equals sine of, or y equals 2 sine of x. All right, so this is a value. This is a coefficient on the outside of my function. I'm going to call that the a value, and that's a vertical dilation. All that does is, on a sinusoid, it's just going to change its amplitude, how high it goes. If I were graphing tangent or secant, those don't have amplitudes, but you take those y values and you multiply by that value. In this case, I'll be doubling all of the y values. Let me write that down about vertical dilations. I think I have it written above me, but I'm going to write it down in my notes as well. a vertical dilation. We simply multiply the y values by a. In this scenario, a equals 2, vertical dilation. We simply multiply the y values by 2. I like to have my students, especially on the transformation homework, identify the transformation, so which variable we're talking about, or not variable, but which transformation we're talking about, A, B, C, D, and then explain in words what that transformation does, draw a parent graph if they need to, and then apply the transformation. So I'm ready to apply. All of the y values will be doubled. Well, the origin has a y value of 0. When I double it, it stays put. This point here, sine is very pretty at pi 6, 1/2. The y value is doubled. So the pi 6 input is not being affected. It's the output. When you double half, you stretch this y value up to 1. Similarly, 1 is doubled to 2. You have, again, a half doubling to 1. And 0 doubled is still 0. So I can kind of see that this shape has remained the same. I still have that wave shape. All I'm doing is vertically stretching this thing away from the x-axis. And of course, the points on the x-axis are stuck or pinned to it. Now I'm ready for my negative values. Negative half doubles to negative 1. There at negative pi 6 and again at negative 5 pi 6. I didn't leave room. But negative 1 at negative pi halves doubles to negative 2. Just barely. I'll make it nice and big. And then, of course, 0 stays put. And so I can draw my sinusoid, or my sine wave. So in orange, I have graphed the function y equals 2 of x. It's simply the y value, it's simply the sine graph, where I've taken the y values and doubled them. If I wanted to talk about certain things like domain, well, that didn't change any. It's still going to be all real numbers. This thing stretches all the way to left and right. Now the range did change. I'm no longer bound between negative 1 and positive 1. I'm now bound between negative 2 and positive 2. The x values did not change. The x-intercepts, sorry. Now my first video, I'm not sure if I liked the way I put x-intercepts. X-intercepts are a coordinate, so I should try to write these as coordinates. So I think if I just say every multiple of pi is going to be a good x-intercept. The way I'm going to write every multiple of pi is pi k. So if k was 0, 0 times pi is 0, I would have the x-intercept 0, 0. Good. If k were 1, well, I'd have 1 pi comma 0, which is labeled here. If k was a negative number, like negative 1, then I would have negative pi comma 0. So k is just some integer value. If I need to write that down, that's fine. K is just some interval. Every multiple of pi is going to be an x-intercept. The y-intercept is obviously 0, 0. And I think I am happy here. Now let's say I needed more than just the pretty points. I know sine of pi thirds. It's not one of the pretty points, but I know that value. It is the square root of 3 over 2. The square root of 3 is about 1.8. Cut it in half. It's about 0.9. I'll go just label that on my x-axis real quick. That is square root 3 over 2. So pi thirds, I have an output of root 3 over 2. Now, if I want to find what happened to this point, well, I simply need to double it. I'll just kind of write down what I'm doing over here. Sine of pi thirds is equal to the root of 3 over 2. 2 times sine of pi thirds will simply be this value multiplied by 2. That's all we've been doing, is we've been taking those y values and doubling them. Taking that y value and doubling it. Well, here the 2 is reduced, and I'm just left with the square root of 3, which is not bad. I'm familiar with that number. That's about 1.7, 1.8. So up here, I can go ahead and, actually, what I should probably do is, because I know the shape, I'll just label the point here, and then come off to the side and say, hey, this is about the square root of 3. So if you're needing to find those other values, you can quickly do so like that. Oh yeah, the period. The period of this sine wave has not changed. I still have a distance to cover of 2 pi before I start to repeat myself. So that horizontal distance has not changed. I still have a period of 2 pi for 2 sine of x. But the amplitude, I think, has changed. Remember, the amplitude is from a 0 position, that maximum distance. So instead of going up just 1, I'm now going up 2. So my amplitude here is 2. And the amplitude will be easy to identify. On sine and cosine, those are the only 2 trig functions with an amplitude. If you have an a value, that a value will be the amplitude. Straightforward. All right. While I have this graph up, maybe I could do a third graph. If you need to regraph the parent on a new graph paper because maybe you're getting too cluttered, do so. I'm going to save a tree and try to graph one more graph. And that was fun, right? Just doubling the y values. But what if that a value was less than 1? Something like a third. So in a lighter green, I'm going to be graphing y equals a third of sine of x. And again, all I'm doing is taking my parent function values. So I am ignoring the orange. That's no longer what I'm looking at. I'm starting over with this problem. I'm looking at the parent graph of sine. I've graphed it from negative pi to pi, showing a full period. And I'm going to find out what happens when I put a 1/3 out front. Well, this is simply a vertical dilation. In green, my a value is 1/3. We could maybe clarify this more. In orange, that was a vertical stretch. In green, this is going to be a vertical compression. Both stretching and compressing, those are dilations, just that stretching maneuver. All right, so a vertical dilation, I'm going to say we need to multiply the y values by 1/3. I think it's going to be quite simple. The 0, 0, 0, the y value 0, multiplied by a third is still 0. 1 should be simple. 1 times 1/3 is 1/3. So I need to label 1/3 on my graph. That's about 0.33333, so somewhere in here. That's 0.5 and maybe here. I label the axes with the exact value. I don't put a decimal value on my y-axis. So I'm not labeling this 0.3 repeated or 0.3234. It's 1/3. And that is the y value at pi halves on the function y equals 1/3 sine of x. Again, the 0 stays put. If you take a half and you multiply it by a third, I think I can do that. Oops. Again, I'm simply taking the y value of the parent sine function, multiplying by the a value 1/3. This gets me 1/6. This is going to be the y value for my green graph at pi6 and at 5 pi6. Instead of going up to a half, I'm going to a sixth. And I have the same shape. It's still the sine wave. It's just going or rising much slower. I've taken that parent graph, and in orange, I stretched it away from the x-axis. In green, I'm stretching it toward the x-axis. Label some negative values here. Do my best to make this curvaceous. Trying to picture a wave. And in green, I have graphed 1/3 sine of x. The period is unchanged, 2 pi. The amplitude has changed. The amplitude will now just be 1/3. X-intercepts, I've listed them. Domain, the range has changed. Instead of being bound from -2 to 2 or -1 to 1, I'm now bound between -1/3 and +1/3. All right, that's vertical dilations if you have a coefficient on the outside of the function. Let's now take a look at b, or if we have a coefficient inside the argument of the trig function. All right, now in this example, let's take a look at that 2 being inside the argument of the trig function instead of being outside. So in black, I've gone ahead and graphed another parent function of sine. That is, I've shown a full period from -pi to pi. I've labeled all the pretty points. Sine is pretty at those sixes, so I've gone through and plotted those and to help me get my shape. In orange, I'm going to graph sine of 2x. Now, the 2 is inside the trig function. This is acting as the b. This is a horizontal dilation. Okay, so I'm going to identify that this is a horizontal dilation. My b value, I'm going to identify it. My b value is 2. And what that does is it's going to take my x values this time and multiply them by not 2, but the reciprocal of 2. That is 1/2. Hopefully you remember these transformation rules from the college algebra setting, and so you kind of remember that anything on the inside of the parentheses is affecting x values, and it also kind of does the opposite of what you want it to do. On the outside, the 2 value, we simply multiplied the y values by 2. And everything made sense. On the inside, we're now talking about x values, and we're doing kind of the opposite. Instead of multiplying by 2, we're actually maybe dividing by 2, but it's the same idea. I need to take my x values now and multiply them by 1/2. So the origin, start there. The x value is 0. I take that 0 value, multiply it by 1/2, it stays the same. That point will remain the same. The pretty point at pi6, 1/2. I'm multiplying the x value this time by 1/2. So pi6 or let me go ahead and write this down. Sine of pi 6 equals 1/2. I'm taking the x value, pi 6. Pi 6 times, that's this 1/2 is that 1/2. Oh, don't get confused there. But anyways, I'm taking the x value, multiplying by 1 over b, and that's going to give me pi 12ths. So instead of moving the y value up and down, I'm moving the x value left and right. Pi 6 has become pi 12ths. Well, that's just halfway. The y value this time does not change. The y value is still a half. It just slided to the left where pi 12ths is labeled. Let's do that again. Sine of pi halves is equal to 1. I'm not affecting the y value, I'm affecting the x value. I simply take that x value, multiply it by 1 over b, and I'm going to get pi 4ths as my new x value. So instead of pi halves mapping to 1, pi 4ths is mapping to 1. Similarly, 5 pi 6 when multiplied by 1/2, that's going to become 5 pi 12ths. It's not labeled on my x-axis, but I can do so. 1, 2, 3, 4, 5 pi 12ths. That's where this new function will hit 1/2. Pi is where it maps to 0, but if I'm going to take pi and cut it in half, so it becomes pi halves. Now pi halves is where it's going to be 0. And I should see that same shape. We're not changing the shape of the sine wave. It's still going to be a sinusoid. It's still going to be that wave shape. All I've done, though, is I've taken that sine wave and I've compressed it. I've horizontally pushed it toward the y-axis. All those points have been halved. Their distance away from the x-axis has been halved. I could continue the sine wave. It would go down, and I think I'd be done by the time I get to pi. But I've shown the interval from negative pi to pi, so I'm going to continue with these negative values. And I already know those values because I did the positive values, so I just have to make all these negative. A negative pi 6, when halved, becomes negative pi 12ths. I think I'll label it up here because I'm about to put a point right there. Negative pi halves, cut in half, is negative pi 4ths. The y value is not changing. I'm just compressing it toward the y-axis. Negative 5 pi 6 becomes negative 5 pi 12ths. Negative pi cut in half is negative pi halves. Try to make this curvaceous, kind of come in and out of here almost horizontally. Make it almost like flatten out there as much as I can. And in orange, I have graphed y equals 2x. All the values compressed toward the y-axis. They were cut in half, 1 over 2, because my b value was 2. If my b value was 4, well, I would be cutting all those x values in a quarter, 1 over 4. Let's see, some things have changed. The amplitude. Oh, nope, that's still 1. I did not change the height of this wave. How about my period? Oh, that changed. It used to take me a distance of 2 pi to repeat myself, but now if I start here at negative pi halves, then I'm going to start going into this negative region again at positive pi halves. So that period has changed. This distance, the period is asking for the distance, not a number, a distance. So this is 1 pi halves plus another pi halves. This is now just a period of 1 pi. Perfect. In fact, Yeah, my x values or my x-intercepts are, oh, they've changed. I'm going to list a good one, and then it's like 0, and then add the distance to the next x-intercept, which is pi halves. Oh, and that's just going to be in both directions. So this is one of the examples where I can just start and say all multiples of pi halves. I'll just test myself real quick. If the integer k was 0, I would have 0, 0, check marks. If k was 1, I would have pi halves. If k was 2, I would have 2 pi halves, which is 1 pi. And yes, this thing is going to hit 0 again at pi. Negatives as well. If you're doing cosine or another one that's not obvious, remember my strategy is you list a good one. So I'm going to put 0, add the distance to the next good one, and put a k on there for every interval. This is typically how I do it. It's just that because we're starting at 0, well, 0 plus anything, that's just going to be that anything. But if you were doing this to a cosine wave, where cosine does not cross the origin, it starts at 0, 1, or it starts high, then you may want to do something like this, where you list the good one and then add the distance to the next. The range is the same. It's from -1 to +1. I think that's everything. Now, I don't have the room, but what would happen if I changed that number on the inside? Instead of being a value greater than 1, like 2, what if it were 1/2? Well, we identify the transformation. It's still b. It's still a coefficient inside the argument of the trig function. It's still going to be a vertical dilation, but I need to multiply by the reciprocal of b. So in green, I have a b value of 1/2, which means I need to multiply the x values by 1 over 1/2, or the reciprocal of 1/2, which is 2. Okay, so I'm ignoring the orange. That was sine of 2x. I'm going back to my original parent, done in black, and I need to take those x values and multiply them by 2. So 0, of course, times 2 is still 0. Let's see, I've got a pretty point at pi 6, 1/2. If I take pi 6 and multiply that by 2, I'm going to reduce that down to pi thirds. So the y value of 1/2 that was at pi 6 is now at pi thirds. Oh, that makes sense. Instead of being 2 squares away from the y-axis, I've doubled it, and I'm now 4 squares away. Let's continue. Pi halves maps to 1. If I take pi halves and double it, I'll be at pi. Yeah, obvious. So pi maps to 1. That was 6 squares away. Now it is 12 squares away. And you can see I'm going to have an issue with the size of my graph. So if you come across one of these in the homework, you may need to start manipulating the scale of your x-axis, or just bust out another sheet of graph paper and really extend out your graph. So here I've graphed a fourth of what I need to graph. I could maybe continue. Let's see, skip, dash, 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 skip, dash, skip, dash, 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 skip, dash. That would get me to 2 pi. But if I take the parent point pi, 0 and double it, that gets me to 2 pi. I can see that, well, let me do one more. 5 pi 6 doubled becomes 5 pi thirds, which is here. Yeah. Oof. Getting kind of rough. But I've got half of my sine wave. I need another half. I need to go into the negative region. I don't have enough room over here into the negative region. So let's tackle that a different way. I need to graph sine of 1/2 of x, and I really should show one full period. So I think what I'm going to do is just change my strategy here. I'm going to create a new Cartesian plane. And some of you may not, feel comfortable with this strategy yet, and if that's okay, I mean, that is okay. Make sure, do the homework like I have been explaining it thus far. But for these longer graphs, see if you can maybe make sense of this. These transformations don't change the shape of the graph. Notice my black and orange graph are still the wave. Even previously when I was doing the vertical dilations, I still have a wave. All three of those graphs look the same. They start at 0, 0, they go up, they go back down. In the left, they go down, come back up. I know what this green graph is going to look like. It's going to start at 0, 0, it's going to go up and come back down. I'm just going to not label my x and y axis. I'm just going to graph the shape of sine. One, two, three, four. I know it's like just even 1, 2, 3, 4. I do know it's symmetrical, so it took me 12 squares to get to this point, and then another 12 squares to get there. So I did the same. I went 4 squares up and then 4 squares down. I'm gonna do the same thing. 1, 2, 3, 4. Came down to here. 1, 2, 3, 4. Down to there. So I've got a lovely sine wave. Now I want to label it accordingly. I have it here in green. I understand what's going on here. The green graph, or sine of 1/2 x, is still going to cross the origin. It's going to hit 1 at pi. So I'm just going to label this as pi, comma 1. It's going to hit the x-axis again at 2 pi. Similarly, looking backwards, at negative pi, I'll be at this negative 1 value, and at negative 2 pi, I will hit the origin again. So I have graphed sine of 1/2 x. That's good enough. I can talk about its amplitude. I can talk about its period. This seems to be a big deal right now because this period was just changed. I no longer have the parent period of 2 pi. How long, what distance does it take me to graph this thing before I start to repeat myself? Well, here I'm starting to go downward. So this is 2 pi, 3 pi, 4 pi, and then I'll be repeating myself. So my period here is 4 pi, which makes sense. Normally it takes 2 pi. With a 1/2, I'm supposed to multiply my x values or my periods by the reciprocal 2, so I can just change my period full on out. All right. If you weren't comfortable with that, that's okay. Put that on, in the back of your mind, start to think about it. But use the transformation rules for A and B to quickly take your parent graphs and start to transform them. And as you do so, ask yourself those same questions. Did this change the period? If so, what is it? Did this change the amplitude? If so, what is it? Are my x-intercepts, were they affected? Did my y-intercept change? Right. I think I've shown you enough. These are old transformation rules. You know these already. All right, go get started on your homework.